recording. Okay. So for people who are watching this, the first review session, welcome. What I generally try to do is I'll try to bring apples later in the semester. It's just too hot to eat apple. I didn't have any. Last year I signed up for CSA. So, but what we try to do here is just, go through problems, okay, and try to find out, where, so it's just like a more intimate setting. So you can ask me questions. I'll walk around, okay? And the plan really would be when I bring apples, today without apples, that you guys, I give you the iPad, you try to solve a problem, we do it together, okay? So we have to move pretty quickly today because I have like 15 problems on there. Many of them are fairly short ones, okay? So that's kind of the plan. So who wants to give a shot at problem number 1? Basically, we're looking for two constitutional isomers, with this molecular formula, right? C4H4. You want to try? Thank you. So try to draw on the iPad. It's not, you can just keep sitting where you
Okay, cool.
And then maybe if you keep talking, it will like record what you say.
Oh,
Explain to people what's going on.
I'm looking for immortality. Maybe this is the ticket. Oh man, I see how you run out of space on this.
Yes.
Challenges.
We can zoom in though. That's what I do in lecture.
Okay.
So this is a great.
I think that's beyond me, but I'm gonna.
No, this is perfect.
Okay.
Okay, perfect. Wonderful. Thank you so much. These are both correct solutions for C4H4. These are all, if you look at these molecules, they have a lot of either double bonds or rings and double bonds combined, right? That's because you don't have too many hydrogens in the molecule. Okay? And so how did you come up with the structure? You just drew, like...
I mean, I did chapter 1.
Chapter 1, you do chapter 1, you practice, you figure it out. It's kind of like, it's like Lego, as we talked about in lectures. Like you just draw, for example, a carbon, and then you can make 4 bonds, right? You just put it together so that it all fits, okay? So we have some more. We'll just keep going through these problems, all right? So we'll go to the next one. So now we have C4H8O2. Anybody want to give it a try? If you just have one isomer, you draw that. That's also fine, right? You want to give it a try? Yeah. Thank you. So hold on. What I'm going to do, because you might run out of space. You see, we can zoom in, and then you can kind of, it's easier to draw a little bit bigger.
I'll try that.
And then you can like move around.
Okay.
And the cool thing is it doesn't move on the screen.
Yeah.
It's pretty cool software. So if you want to go back and undo, you can just click on this one.
Okay.
That will undo it. Yeah.
I was looking at both of mine at once and started doing the wrong one.
See, yeah. So you need 2 oxygens. Yeah, perfect. So let's see. We want to so you can also move the molecule. Let me show you. You can select it. It's a little bit too much to the left, so we're gonna. It's kind of a lesson on
this is
iPad
cool.
drawing. You can just move it over. It's pretty good. Exactly. I think that's right. We just count the hydrogens, right? So we have how many? 1, 2, 3, 4, 5, 6, 7, 8. Perfect, right? So the important thing, I'll talk very loud so people can hear it on the iPad. Thank you. The double bond here is important, right? Because if you don't have the double bond, you would have 2 more hydrogens, and then you have 10 hydrogens instead of 8, okay? So you see, if you have too many hydrogens, just put in an additional double bond or a triple bond, or make a ring somewhere, right? That's the general rule. Okay, good. So we need another one, because it asks for 2 constitutional isomers. Anybody has another one? Okay, great. Thank you. Okay, so let me show you. We can zoom in, right? Okay. If you like. If you draw small, you can probably just draw there. Yeah. This is called a peroxide. This is good. These are like radical initiators. Don't worry about it. They're useful to make like polymers and stuff. Perfect. Thank you. Right? Tell me your name.
Emma.
Emma, so what Emma did, right, she took the double bond and converted it into a ring. Okay, and then that gives you the same molecular formula. Perfect. Let's just move on, right? These are fairly, mostly Gen Chem reviews still, right? I think is this the last one of one? Oh, there's one more? Okay, so we'll keep going. Anybody wants to try to draw on the iPad?
Can you go back a bit?
Yeah. Let me do this. I will try not to, let me see. I think if I click here, no. Hold on. I think I clicked the wrong button. Now it opened up a new window.
Okay.
Sorry. I can, why did that happen? Oh, yeah. There's two buttons. If I press the upper one or the lower one, it goes, we'll try it again later, okay? If you copied from your name, I'm so sorry. Okay. We can go back and watch the video later. Okay. So I need another volunteer for the next one. Yes, please. Thank you. I'll try to figure out these finicky things. This going back is hard. If you press the wrong one, it just goes out of the program. C4H9N. Perfect. Do you have a second one you want to, or we'll get somebody else. That's fine. Thank you. Anybody want to try the next one? Yes, please. Okay. Here. Thank you. Okay, so thank you so much. So here there's one sticky point now. Okay, so whenever you draw, it's fine. Don't worry. That's what, like, you see that here's the thing is we do this together, right? So we learn. So you see what? Do you see what could be the problem?
Now the carbon is
the
violating
carbon,
the octet
right?
rule.
So you see, I'm going to highlight it. This carbon here is violating the octet rule, right? So that's when I saw you draw the triple bond, I realized there might be,
it's not gonna
right? But we can easily fix the structure. Okay, I'll make a few minor changes. So what you need is, for example, we convert this into a double bond, right? And then we make the octet rule. So we take off one hydrogen. So now the octet rule on the carbon is okay, right? Carbon is okay. And now we can introduce an additional hydrogen here. Okay? And so now it's fine. So see that you start to see the general strategy now of how we do this stuff, right? We basically have, when you have, for example, you can figure out how many hydrogens are missing compared, like the maximum amount of hydrogens you could have in this structure, right? With 4 carbons and 1 nitrogen would be really 11 nitrogens. If you have no double bonds or rings, 11 nitrogens is the absolute maximum of hydrogens you can have, right? So if 2 hydrogens are missing, that means you must have either 1 double bond or 1 ring, okay? And so what we have done from the structure to the left to the right, those 2 structures, they just have the double bond in a different position, right? And you can draw many other structures which have double bond in different places, okay? But you need at least, or you could make a ring, but you need 1 double bond or a ring. So if you put a triple bond, you will have 2 hydrogens missing in addition to this. So you would only have 7 hydrogens, right? So then it doesn't fit. Or if you have a ring and a double bond, you have only 7 hydrogens. You see, that's a general pattern. So you draw one structure. As soon as you have one isomer, the second one is easy because you just move the double bond or the ring things around, okay? Good, let's move on.
I have a quick question.
Yes, please.
Would you want to draw the lone pairs, like lone pair of electrons on those?
We would want to. So let me try to go back this time. I think I need to push this button. Yo, it works. Okay, yeah. I just need to push the right button. So yes, we would want to. You're right. It's better to draw the lone pair of electrons, at least for now. Like later in chapter 2, we'll start to drop lone pairs. They will be implicit, which means you should just know where they are. Okay, and we'll completely stop drawing carbon atoms. That makes your life harder, but it makes it easier to draw, but it makes it harder to recognize what's going on. But for now, I would recommend you draw the lone pairs, okay? Good question. So we move back forward. One more. I think this is the last one. Yes, please.
I'm going to do it.
You can do it? Okay, thank you. Let's go for it. Thank you.
Thank you. Okay. Ooh. Oh, my C is really ugly. Sorry. Oh, where am I looking? 1, 2, 3, 4, 5, 6.
I think this is correct structure, right? Thank you so much.
So.
So in general,
Oh, sorry, my letters are really ugly.
that's okay. I'll do a little bit of. It takes a little bit of practice to draw. It's kind of like when you sign in the supermarket, but it's better with the. First, I tried with the iPad Generation 1. It was really bad. This is like the iPad Pro, with there's an Apple Pencil. It works much better, believe me. So here's the thing. In general, when you draw structures, right, over time you will develop a sense of what are very stable structures and what are not so stable structures. So things like this, where you have double bond after double bond, these structures exist, but they are really not very stable. Okay, they're called allenes. We'll talk about their orbitals in a while. Like what is the hybridization on these carbons? What sp on all of these guys you see in the middle? For example, this one here is s. So this is actually sp2 hybridized. But then this, so you were right. So this is sp, right? This is sp. Okay, because you see here the steric number is just 2. The steric number is just 2, right? So these are all sp hybridized, and yeah, I'll upload this video which talks about how the orbitals are aligned in that case. It's really, they're all orthogonal. They have these p. It's like a linear. It's like it looks like a stick. This molecule, okay, and it's really unstable. Very interesting molecule, though. So the other thing is an oxygen double bond. In general, it's called a peroxide, as I mentioned before, and it breaks apart really easily. It likes to go from. So if you have something like this, oxygen, and then something attached here and here, it really likes to. For example, if you shine light on it. What it will do is whatever is attached here will make a radical. It's called a radical, just like it breaks apart in half here, and it makes 2 out of these. And then these things start to react. So for instance, in the body, if you have this in your body, it will start to react with your proteins, and that's why people get sick if you eat chemicals like this. One common thing is in acne medicine, which people put on, which bleaches everything, and that stuff also is a peroxide, and it kills all the bacteria, and but it's really, that's why you put it on your skin. That's kind of how it works. So in general, while we proceed, we'll start to draw more and more stable molecules. Okay, so I'm going to give you so one more stable molecule. For example, for this case, a really stable one would be something which has a ring, a 6-membered ring. Sorry, I'm drawing this without carbons. This is bad. It would be something like this. I want to do one myself, so I'm gonna see. You can put this kind of ring is really stable, where you have 3 double bonds. It's called an aromatic ring. You will talk about them in the second semester a lot, and then we can have each carbon is sp2 hybridized. For example, you can have an OH here, and you could have another OH. Right? We need 2 OHs. Then we would have hydrogens here. Is this correct? Let's see. C6, O2, 1, 2, 3, 4, and 6 H's, right? So that would be that's much more stable than the molecule on the left. But these are all great examples. So any questions about these things? Just keep practicing. Okay? Yes, please.
So it's okay to make any structure right now as long as the formal charge works out.
Yeah. So the question is, I'm just repeating for the, is it okay to draw any structure as long as the formal charge works out and it's correct? Let's say you have an oxygen-oxygen double bond. It's not the most stable structure. Yes. I will not penalize you for drawing these are perfectly reasonable structures. They're interesting in their own right. I'm just trying to give you some feeling, because otherwise it's kind of boring material. Okay? So yes, the answer is yes. As long as you draw a correct structure, that's fine. Okay? So this one. So we are at question 2. What is the relationship between these two compounds? Any thoughts? Yes, please. So yeah, they are the same molecular formula, right? So what's the molecular formula?
C3H8O.
Yes. Molecular formula is C3. Again, remember, you do C, H, and then O, right? And then alphabetical. So CH and then alphabetical. So C3H. How many H we had? 1, 2, 3. H8. Yes, and then O. So they are the same. They have the same molecular formula, right? So what's the relationship then? The relationship means like what kind of isomers are there? Are they isomers, and or what kind of constitutional isomers, right? And again, so far we have only seen constitutional isomers. So it's, as long as they have the same molecular formula, great. Again, in chapter 5, we will see lots of different isomers, like stereoisomer, diastereoisomer, enantiomers. It's going to get much more complex. So it's good to be really solid on the constitutional isomer side, right? So what do we say here? Just say like this. I'll write this myself, right? You guys can. That one is not. It's more interesting for you guys to use the iPad if it's a structural drawing. Otherwise, I can just do it. Constitutional isomers. Okay. Good. And any questions about this part? Make sense? Okay. So then let's go to the next one. Similar question, right? I gave you a bunch of molecules. Which ones, molecules 1, 2, 3, 4, which ones are constitutional isomers and which ones are not? So what you have to do here is just pretty much write down the molecular formula for all of these things, okay? I think it's AE in Latin, right? So why don't you guys write the molecular formula? Can you try? You want to try for the first one, or?
I don't know.
You want to do it together?
Good for this one.
How do you? We can do it like spontaneously. It's up to you. So how do you do it?
Not this one.
Not this one. Okay, you can do it. No, that's fine. The way we do it to get a molecular formula is just you count the number of carbons, right? And then you count the number of hydrogens, and then you count the number of all the atoms. You just put it alphabetical, and right. That's it. So anybody wants to write? Yes, I'll go. And you guys can just hand the iPad around and then just write.
Okay.
I think the easiest way to do it is just write the molecular formula underneath each structure, and then we can just see which ones are constitutional isomers.
So just write it on one of them?
Yeah, maybe just underneath. Or, on the side somewhere.
Okay.
Perfect. Good. Thank you. Perfect. So these are the same. They're constitutionalized. So, here's the thing, okay? This stuff is fairly simple to do, right? But what happens to people, including myself, is you take an exam, and suddenly you are nervous, and you miscount, and you lose all bunch of points, okay? Like, this happens to people, okay? It's very common because at the exam you're nervous, you might be running out of time, or you're just having a bad day. So that's why you need to do exercises so that you practice this stuff. You make yourself you get some sort of your own routine of doing it. Like when you brush your teeth, you make sure you don't forget one side. Okay? So you count in a specific way. Maybe use your finger, or something, or underline the atom when you've already counted it so that you don't double count. And things like that. That's why it's important, even for the simple stuff, to do a bunch of exercises. And you can kind of do it in your sleep. And because an exam in the end, what it really is, it's just collecting points. It's like you're in a casino and you just collect as many points as possible. Right? And it's as simple as that. It's not the optimal way to test your guys' ability of doing organic, but it's the best we can do, right, to assess your performance. And we have to do it for the grade. Can't give everybody an A. But so practicing the stuff. So you get all the points on the simple stuff, and then you can do those problems quickly, right? That's the other thing. If you can do the simple problems relatively quickly on the exam, it leaves you with more time, and it gives you for the harder problems, and it gives you a much better feeling. Because I'll try to at least I try to do it, put the simpler things at the beginning, so you can kind of tick them off, and then you are like, okay, I already finished 50% of the exam, and I have a pretty good feeling what's going on. And then when the harder problems show up, you're not like completely freak out. Because the worst thing that happens to you, that happens to me once in a math exam. It's like I did this and I couldn't do the first problem and then the second problem, and it was like, and then you start to your brain starts to shut down and you feel really bad. And at that point you have not much of a chance of catching back up because you need to calm yourself down. It's like the adrenaline comes out of your body and you can't think. All you want to do is run away, okay? And so that's why you need to be very solid on the simple stuff to kind of get yourself calmed down. It's more of a strategy of taking exams, but practicing it helps. So if you have a bad day, winter is coming. Flu season is coming. Seriously, flu season is coming. Lots of exams are coming. It's going to be tough, okay? And it is. And so you need to do these exercises. That's if you prepare really well, you shouldn't have any real problems on the exams, okay? All right, so we are done with this. We circled the ones which are constitutional isomers, so that's it, okay? The more important part is my exam. Blah, blah, blah here, okay? So let's go to the next one. This is more interesting. So what's the correct Lewis structure for this molecule? And particularly, why are the other Lewis structures not correct? Okay? So what happens here is, essentially, all of these Lewis structures... is there anyone in here which does not fulfill the octet rule, first of all? Which ones? Which one? Oh, for example, 1, right? There's like this does not fulfill the octet rule. And 3. Yes, that's right, here, right? So those are not that great, okay?
2 and 5.
And 2 and 5? Okay, yeah, 2 has, this is bad, right? This does not fulfill the octet rule. And 5, where's 5? Oh yeah, 5 is one on the oxygen here, is too many, okay? So I'll put some, I don't know, we'll just cross these out, or we can put like some, we can do these faces here. I don't know, and then copy this face a couple times, I don't know. Copy, and then we can paste it. Look. I'll draw these faces if I grade the exam. Okay, so these are all bad structures. It leaves us with one good structure. Okay? And does anybody know? So that's the correct Lewis structure. Does anybody know the name of this molecule? It has a carboxylic acid, yes? So this is called acetic acid. That's basically what's in vinegar. That's vinegar. It's just, this is by itself, it's very strong. You can buy it, I think, in Lowe's, or Home Depot, and you pour it in your toilet, and it will clean up your sinks or your drains. But it's very strong. And normally, what's in vinegar, it's like a 2% or 5% solution, right? But it's very it's an acid, so it's sour. So it's acetic acid. Right? But you see, what's important here is not necessarily what's the correct solution. It's also, the problem-solving strategy, how we go through this. So you look at the different structures, and there will be, at the beginning of the exams, I'll put a few multiple-choice questions, just so that, exam grading becomes a little easier. and then the rest of the exam will be all free form. But it's not necessarily that the free form stuff is much easier because you have to draw. Okay? So, but in a multiple choice thing, you have to just, you really go through answer by answer and try to find out, which structure is wrong, and why it is wrong. Right? Don't just guess. Like really find reasons for, and look at every answer very, very seriously. Okay? Or work out the problem by yourself. For example, the other way to approach this problem is you just try to draw a structure for this molecular formula and figure out what structures you can come up with. Okay? Any questions about this one? Good. Okay, let's move on. Okay, now we're getting to some problem 5. So this is all about formal charges. Okay? On the boron and oxygen. So somebody can write the charges if you guys want. Or, yeah. You can do maybe the oxygen and then she can do the boron. Okay? -1. So can you explain how you got to -1?
Because boron is in group 3, which means that it likes to be 3, right?
Yeah, so boron is in group 3, so in neutral form it wants to have 3 valence electrons.
So
right
now it has more than that. So more electrons is more negative.
Yes, so now it has 4 electrons, right? Because we take each bond the boron makes and we split it in half, right? So the boron gets 1 electron out of each bond. So it means it has 4 electrons. It wants to have just 3. So it has 1 electron too many, and so it's -1. Okay? Thank you. So the oxygen, yeah, you want to draw, or you can just tell me. I can just write it. It's +1, exactly. And the reason, right, how many electrons does oxygen want in the neutral form? 6. So it's in group 6, so neutral it wants 6 electrons. And it has, like, each bond again is split in half. So it gets 3 electrons from the bond, from the 3 bonds, 1 each, and then 2 electrons from the lone pair, so it has 5 electrons. So it's missing 1, so that's why it's +1. Okay? So that's the formal charge thing. What you want to start to do as well, over time, and we'll talk about this, I think, some more in chapter 2. You want to start, you see, when you have a complex structure, like a whole antibiotic or something, I showed you some really complex structures at the beginning of the course. If you have that, you can't really practically think about each atom, how many electrons it wants and how many, it has. It will take you forever, to finish the more complex problems we'll have down later in the course. So what we are going to do is eventually we are going to just recognize the pattern. Right? So what we're going to see down the road, and when you start to do exercises, your problems in the book, you will get the hang of this because it's always the same pattern. So for example, if you have an oxygen with 3 bonds and 1 lone pair, it's always +1. If you have a sulfur, which is the same group, with 3 bonds and 1 lone pair, it's always +1. If you have an oxygen with 1 bond and 3 lone pairs, it's always -1. Right? And then a boron with 4 bonds and no lone pair is always -1, etc. So you will start to recognize these patterns. There's about 5 or 6 of these patterns, and we'll write them all down in lecture, and that will make your life much easier because you don't have to do this whole calculation, splitting the bonds and right anymore. Okay? So start to practice that as you go through the problems. Okay, so next one. Now these get more interesting. So which is the correct Lewis structure with formal charges? And why are the others not correct? So let's just go through structure by structure, right? And say why some of these structures are bad. So structure number 1. The formal charge on the nitrogen is correct, right? Because nitrogen group 5 wants 5 electrons, has 4 electrons, you split all the double bonds into half, so 2 and 2, that's 4, so it's +1. What about the oxygen on the right? So we're talking about structure number 1. Right? The oxygen on the right, the formal charge is correct. So nitrogen formal charge is correct, oxygen formal charge is correct. What about the nitrogen on the left? What's the formal charge there? -1, right? So this is -1. Sorry, I drew it over the lone pair, which is kind of silly. So this would be -1, and so this structure is not correct because the -1 is not drawn. Make sense? So next structure. Nitrogen again has 4. Whenever you have a nitrogen with 4 bonds and no lone pairs, it's +1, right? So that formal charge on the nitrogen is fine. The nitrogen on the left is fine, right? and the oxygen on the right is fine. Okay? So this is fine. Right? So this is correct. Now let's look at the other structures. Right? Let's see. What would the structure number 3, what's the formal charge? So first of all, what about octet rule? The central nitrogen does not fulfill the octet rule, right? So this whole thing is bad. Okay? See, I can still paste my face here. Okay? So, no, I just like to play with the iPad. I think it's cool. I think it's better than the board. It's like, it saves the stuff. What we can do down the road, okay, is if we draw really complex mechanisms, I probably won't do it because it's not so fair for you guys to follow me. I can draw a structure, and then I can copy it. It can be really complex. You paste it, it goes, and I can draw really quickly. But I will try to draw it manually so you can see what's going on. Otherwise, you don't have a chance to follow. That'll be too fast. So the next one, right? Octet rule is fine for all the atoms. The formal charge for the oxygen on the right, so this one, is fine, right? Because it's again 3. What I said, 3 lone pairs, 1 bond. Oxygen is -1. So this is fine. The nitrogen in the middle, fine. Okay. The nitrogen on the left, not fine, right? Because it's -1. It's the same as what we had over here. Okay. Ooh. Okay. Sorry. So that means one thing is wrong. So that's bad. Okay. That rules it out. The last structure. Let's see, number 5. Oxygen to the right would be +1. Because now that's an oxygen with 3 bonds, 1 lone pair. Nitrogen is fine. And the nitrogen on the left is also wrong because that would be 2-. Okay, so that would be 2-. Okay, so you see so essentially this problem is if you can really figure out what's wrong with all of these structures, you're in good shape. Okay? Any questions? Make sense? It's really just like practicing, this thing, formal charges and Lewis structures, octet rule over and over again. Okay? Let's go to the next one. Okay, NH2CN. Anybody want to try? So that's something you guys can try to draw. You want to give it a try? Thank you. So we have, does this belong to anyone? Oh, okay.
Yeah.
You're welcome. Let me check. Whenever I go to CNN, there's always, regardless of what happened in the world, there's always a picture of our president in the front. All right. Thank you. This is perfect. This looks great. Okay? Any questions about this structure? Looks great. It fulfills the octet rule. There's really, yeah. There's not too much to say about it. Okay? I'll try to find something to say about almost anything, but there's really nothing to say about this one. Okay? Let's continue. So, now we're getting into quantum mechanics, okay? This was something I talked about in a video. And so it's good we talk about it briefly, I think. So quantum mechanics, again, what's quantum mechanics? What is it used for? It's this theory which describes electrons as waves and which gives us the output of quantum mechanics. It's actually the equation which is used called the Schrödinger equation. You might have heard of Schrödinger. He's a famous guy in physics, okay, 1920s, and he Erwin Schrödinger from Germany, and he came up with the Schrödinger equation. The output describes orbitals. That's where the electrons are, right? And in the video I talked about these orbitals essentially describe the probability, or the square of the orbitals, which is the electron density, describes the probability of finding an electron within that orbital. Okay? So, and now this orbital, essentially what it is a wave function, right? It's the electron is the wave, and it's where the electron is. And so that's usually abbreviated as this psi. Okay, that's this Greek letter here. So this is essentially, it's just the orbital. In chemistry we call it an orbital. In physics they call it a wave function. It's the same thing. So now, yeah, we've talked about nodes, right? So we can draw, I'll give you an example. The one I put in the video, I think, was a p orbital, right? And it looks like this. Remember, it looks like a dumbbell, has a left part and a right part, and I drew it in red and blue. And so the blue part was the positive part, right? So we'll say psi is larger than 0. And the red part was where the wave function is negative. Okay? And now where is the node? The node is in the middle here. There's a nodal, it's actually a nodal plane, right? Through the middle, where the wave function is 0. And so that's the node. Okay? And so in general, what we'll see is the more nodes or the more nodal planes you get, the higher in energy the wave function is. Okay? That's why, for example, an s orbital, remember how an s orbital, so this is a p orbital, right? And you talked about these orbitals in Chem, right? So just a review. So a p orbital looks like this, and an s orbital looks like this. So like a sphere. So how many nodes does an s orbital have? None, exactly. So that means, you see, that's lower in energy because it has fewer nodes. And then then there's also d orbitals. They look different again. They have like 4 lobes, so they have 2 nodal planes. And so that's a useful thing to know. The more nodes, the higher in energy. It's always true. Okay? Yeah, I don't want to tell you now why. Has something to do with the curvature of the orbital, and it's essentially the kinetic energy, which is the second derivative of the wave function. So don't worry about that. If you ever take a quantum mechanics course, you'll learn about it. Okay? And any questions about this? So answer which is correct is E. Okay? The node is at the location where the wave function of the orbital is 0. Where you switch between positive and negative parts. Okay? Sorry, any questions about this? Or that's fine. Good. So this is an interesting one. This is about dipole moments. Okay? So you see that the question is why you see carbon-chlorine bonds are really polar. And so phosgene, which is really a very toxic gas, it's kind of like those nerve agents people use, because the carbon-chlorine bond is so polar, so it reacts with proteins in the body and cross-links them. And then, that's bad. That's very bad. And then formaldehyde, which is also toxic, it's used in polymer composites, like stuff you put on your walls when you build a house. And so that's why you need to let the house degas first. Let it air it a little bit after you paint, because it's not good for you. Okay? Okay. So anyway, so why is it that phosgene, even though the carbon-chlorine bond has more polar bonds, it has actually a smaller dipole moment than formaldehyde? Why is that? Yes.
Is it because the chlorine, 2 chlorines, like the dipole moment gets split between the 2?
Yes, it's because, remember that the overall dipole moment is the sum of the individual dipole vectors, right? So let's draw all the dipole vectors for each bond, okay? And then you're right, it's because they add up, they cancel each other out in the phosgene case, okay? So let's just do it. What I will do is I will draw the individual bond dipoles in light, like orange, okay? And then the overall dipole in red. So the carbon-hydrogen bond is almost, the electronegativity of carbon and hydrogen is almost the same, so we can pretty much ignore the dipole moments for the carbon-hydrogen bonds. Okay, we'll assume there's no dipole moment there. So, but for the carbon-oxygen bond, again, we have a delta plus on the carbon, delta minus on the oxygen. So here we have a bond dipole like this. Okay, and now, of course, so what I will say is this, I'll make a legend here, that this equals bond dipole, okay, and the overall dipole moment we'll do in red. Okay, so this equals the overall dipole moment, which of course is the sum of these ones. We can draw it like this, these I, okay, these individual dipoles, okay? So this is our legend. And so now the overall dipole moment in the formaldehyde case is just the same as the individual bond dipole. There's no other dipoles, okay? So I'll just draw that here. But now in the phosgene case, Now you have dipoles, they look like this, and like this. Okay? So if you add them up, you get something very small, which might look maybe like this. You see that? Because the dipoles are pointing in opposite directions. They cancel each other out. Okay? Whether it points up or down, I don't know exactly. It depends on the actual polarity. Question?
That's
Yeah.
what I was going to ask, if the costume was going to actually tilt.
If it points down or up, yeah, towards the... So this is a great question. It depends a little bit on the magnitude, right, of how long these individual vectors are.
Yeah.
And I just simply don't know the answer. All I know is going to be the dipole moment is going to be small. So in an exam, as long as you explain to me that's what's happening, that's fine, right? You don't have to know whether it's pointing up or down. Yeah.
So with a question like this, would a drawing like this be enough explanation, or would you want us to write out like because they add up and cancel each other out?
So yeah, I'm just going to repeat the question for the iPad. The question is, on an exam, what do I want? Do I want, for example, you guys to write a sentence saying that, because the dipole moments cancel each other out in the Faustian case, or is a drawing fine? A drawing is always, generally I prefer drawings, but you have to make sure that they are clear, okay? So for example, if you, actually the best thing to do is put a drawing and then one sentence, right? So that it's absolutely clear that you really know what's going on. Like in case, and that's going to cost you like half a minute to write down the sentence. So in case of doubt, put a little bit extra information. But in general, it doesn't help to, write like a page. It's not necessary, right? In general, there's a clear reason for what's going on. You just have to hit the right point. And as soon as, like we'll grade this, the TAs and me, right? I'll grade it myself. And if there's any question of that, we'll give you the points, as long as it looks like you really know what's going on. It's usually pretty clear if people know what's going on or not. Okay? Any other questions about this dipole moment thing? Okay, so let's move on. Let's see. So I think we're getting slowly towards the middle or end of this thing, right? Yeah. Okay. Sugars. So this is all about solubility, but it's also related to the interactions, the intermolecular interactions we talked about today. Okay, so sugars, this is a typical sugar. It's obviously important. It's sweet and it's, it plays a huge role. Why are sugars important in the body? Besides glucose, yes, it's basically what the brain runs on glucose, right? That's the only thing the brain can use to run with. Okay, other organs can use other kind of like fat and things like that, but the brain can only use glucose. So very important. That's a sugar. Now, but the other thing which is important is sugars. Like sugars can be linked together into like little polymers, or oligomers. It means just a bunch of sugars together, and they get branching and stuff. They sit on the surface of all the cells, and that's how the immune system, or the cells in the immune system talk with each other. So if for example, you have a virus in your body, or a bacterium which has different sugars on the surface, your immune system will recognize that sugar pattern. There's like these biomolecules, and they will recognize the sugar pattern, and then that like tells like the T cells, the cells which are supposed to kill the bacteria, they will mobilize them, and they will go and eat the bacteria and keep you alive. Okay, so that's how it works. Or for example, the immune system will recognize a cell which has a virus in it and is infected, and they will kill that cell so that the virus can't keep spreading. Right? It's very important. It's all sugars, sugar chemistry, very important. But for now, first of all, this is also important for biology, and sugars are obviously soluble in water, because the whole body is full of water. If the sugars aren't soluble, then everything wouldn't work. Okay? So why are they soluble in water? What interactions keep them soluble? If you look at this, see, there's a lot of OH bonds. Okay? Lots of them. Lots of OH bonds. And what are OH bonds good at? Yeah.
Well, water is a polar molecule, and so is sugar because of the H bonds.
Exactly, H bonds. It's all hydrogen bonding. Okay? So what happens is, think about, you put the sugar in water. I'm going to make the waters all blue. Okay, so we'll have a water, example here. Right? And of course, all the waters, sorry, that has two oxygens, two hydrogen. So all the waters themselves are are hydrogen bonded. Let me try to draw this a little nicer. So, right, all the waters themselves, they're hydrogen bonded. So here would be a hydrogen bond. And then the OH here can form a hydrogen bond. And so you can have either the oxygen or the hydrogen of the sugar, bind to a lone pair of the water, or you can also have, then you can have two hydrogen bonds. For example, you have another water here, where now the hydrogen of the water, interacts with the lone pair of the oxygen. Right? So you can make a lot of hydrogen bonds and really nicely embed this sugar in the water. That's why it's soluble in the water. Okay? So the answer is really hydrogen bond. Okay, any questions? It's pretty straightforward. Okay, now this is related, so we have question 12. This is related to what we pretty much ended up in lecture today, right? About, so first of all, what kind of interactions, when you look at a question like this, which molecule has a higher or lower boiling point, you have to first look at what are the predominant interactions which keep the molecules together, right? And so you look at the strongest interactions first. So for example, here, do we have hydrogen bonding? No hydrogen bonding, right? So do we have dipole-dipole interactions? No, because there's really not much. Before we just said carbon-hydrogen bonds are almost carbon-hydrogen, almost the same electronegativity, so not really much polarity there. Okay? So what interactions are we left with then? Dispersion interactions, exactly, or van der Waals interactions. I don't care how you call them. Either way. Okay? So dispersion or van der Waals interactions. And then we go to the rule, which we talked about, the rule of thumb we talked about in lecture, which is the larger the surface area, right, of a molecule, the stronger the van der Waals interactions. I gave you this analogy with my funny computer bag. Okay, on the table. but you get the point, okay? And that means we also said another rule of thumb is the more branching, right, the more spherical a molecule looks, the less the van der Waals interactions. So which one is more branched, 1 or 2? One is more branched, so it has a lower or higher boiling point? Lower boiling point, right? Because it has weaker van der Waals interactions. So the stronger the interactions, the more energy you need to put in to make the molecules break apart. So the lower the boiling point. What did I say? The higher the boiling point. Okay, sorry. So let's see, we're going to circle higher boiling point, so that would be this guy. Okay? And the explanation would be 2 is less, branched, and then therefore it has stronger van der Waals. Well, we called it dispersion, whatever we call it, dispersion forces, and that means high boiling point. BP. Okay, good. Any questions?
I think
Yes.
skip number 11.
Did we?
Yeah.
What was 11?
Which of the following compounds is most soluble in water and why?
Oh, let's see if I have a slide on it. Did it show up on here? Yeah, maybe. Oh, let's see. Maybe it comes after. No. Yeah, so I probably just forgot to put it on here. Yeah, it's just missing on here. So 11. Let's see which compounds were there. Let me see. Oh, there's a lot of compounds. Okay. Let's see. Okay, so we'll just do it like orally. I don't want to draw them all on the iPad because you guys all have the handout, just for people who are listening in on this thing. So there's 4 compounds for number 11, right? One is just only has CH bonds, okay? And then that's number 1, compound number 1. Compound number 2 has an OH bond, right? And so that's obviously that you should see like hydrogen bonding immediately. right? And then we have number 3, which is has no hydrogen bonding capability, and number 4 also has no hydrogen bonding capability. Now, whenever you look into solubility in water, hydrogen bonding is really key. If you can't make you can't make strong hydrogen bonds, it's a problem. Okay, so the one which is probably the most soluble is the one with the hydrogen bond. So number 2, which is the one you saw. Okay, so 2 is the right answer. Does that make sense? Sorry, I skipped that one. I think I didn't put it in the iPad. In the future, what we're going to have is fewer questions, but harder ones. Okay, that's just chapter 1 because it's a lot of review, so we just go fairly quickly. Future will be like more will be different. So now we are at 13, or we did 12 already. Okay, so we are at 13, which is the strongest intermolecular force present in the following compound. Right, and so we have what is it? What do you guys think? Dipole-dipole, yes, because so you actually so you have the SH bonds, right? The carbon, sulfur, and SH. So you see the SH bond. Sulfur is still fairly electronegative, so you could still call it a hydrogen bond. Okay, but if you don't call it, because in lecture I said OH, NH, and FH are really the very clear, the strongest hydrogen bonds. So this is kind of the SH bond is kind of in between a hydrogen bond and the dipole-dipole interaction. So whether you call it dipole-dipole or hydrogen bond, I think I would give you, in this case I would give you points in either case as an exam. Okay, so I'll just say dipole-dipole, dipole-dipole, or H bonding would also be correct. Okay, next one. Okay, BF3, right? There's no dipole moment. Draw the Lewis structure for BF3, show all non-bonding electrons, and then indicate the polarity, and explain why it has no dipole moment. So somebody can do this. You want to try? Yeah. Thank you. I'll switch back to black here. Thank you.
Ooh, let's see if we can do this. Right.
Is this the last question? There's one more, right? Oh, 16. Yeah, we're going to say we do 16 and 17 next time. Because you need to know a little bit more about my video, which I'm going to upload tonight for tomorrow. So we just one more after. So it's good. Perfect. So these are the individual bond dipoles, right? And now you see that, what's the geometry on the boron here? It's trigonal planar, that's right. Right? Why? Because that's exactly right. Trigonal planar. Very good. So why? What's the steric number on the boron?
3.
Steric number is 3. So what's the hybridization? sp2. Yes. It's sp2. That's right. And so, yeah, so it's trigonal planar. That's important. Because if it's not trigonal planar, and if it would be trigonal pyramidal, then you would have a dipole moment. Okay? Because if it were trigonal pyramidal, for example, you can have ammonia, right, which looks like a pyramid. There you have bond dipoles, but then they don't sum up to 0, right? Because they are in the third dimension, they are not zeroing out. But here, because it's trigonal planar, they're all in the same plane, so it cancels out. So the geometry is really important. Yes, please.
How do you know that boron is the delta positive and fluorine is the delta negative?
It's a very good question. How do we know that the boron is delta positive and fluorine is the delta negative? Yes?
But it has to do with the electronegativity, so fluorine is way more electronegative, so it's going to drop the electrons.
Yes, so fluorine is more electronegative. But let's say you don't know the electronegativity of all the atoms in the periodic table on the exam. What are you going to do? You look at the periodic table I give you. I will give you a periodic table, I think, with electronegativity. And if I don't, then just ask me. Okay? But I think it's already there from last year's exam. I'll just copy it. So I try to give you those tables. I think the book has a table, right? I'll try to give you, at least I'll give you a periodic table which has like the atomic numbers, the masses. You don't need the masses and stuff, but which has everything in it. As long as you know where to find the stuff in the periodic table, you're good. The other way to know it, right, which is my preferred way of you figuring it out, it has something to do with the trends, okay? And I think I talked about them briefly in one of the videos. So essentially what happens if you go from left to right in a row in the periodic table, the electronegativity increases. Do you guys remember why?
Atomic size, Z effective.
Yeah, so the Z effective, the charge, is getting higher because whenever, you're getting more, going to the right, you're getting a higher nuclear charge, right? But of course you're also adding more electrons, but you're adding the extra electrons you're adding, they're all going into the same shell, okay? And so that means the shielding of those electrons, those additional electrons, the shielding effect is smaller. It's not really there because they're in the same shell. And so the effective charge gets higher, and so the electrons get pulled to the nucleus stronger, and so the electronegativity increases, right? And if you go down in a column, the electronegativity decreases because the electrons get pulled into higher shells. The valence electrons are further away from the nucleus, and so then the electronegativity, they're pulled weaker because the Coulombic interaction is dependent on the distance. You're further away from the nucleus, you don't get as much nuclear charge to pull you there. Okay? So those are, you either know the trends or you look at the periodic table in the exam. Don't forget to look at the information I give you at the exam. Okay? Okay? So it averages out to 0. Bless you. Last question, right? So we have boiling points here for trimethylamine, ethylamine, and propylamine. And you see the molecular formulas or formula for these compounds are all the same, right? So they're all constitutional isomers. Am I right? I think that's right. Right? They're all constitutional isomers. But you see the boiling points vary dramatically. I mean, by 50 degrees, that's a lot. Why? Yes?
Because, so as you go from left to right, so like trimethylamine has no hydrogen bonds, and then ethylmethylamine has 1, and then propylamine has 2.
Exactly. It's all about hydrogen bonds. Absolutely right. So trimethylamine will say no. It has no ability to form hydrogen bonds. This can make 1 hydrogen bond, depending on how you count. But I mean, you have 1 NH and 1 lone pair, right? These can all engage in hydrogen bonding. And then here you can form 2 hydrogen bonds, really. Okay? I'll put these in quotation marks because, again, it depends how you count. Like I think about it, if you think about like in the water case where the NH can both act as a donor of a hydrogen bond and an acceptor, then you have actually 2 in the case of the, okay? So, that's pretty much it. Thank you guys for coming, okay? See you guys next week. So we'll try to do this every week except when there is an exam. Then we'll do the exam. Yes, please, one more question. We can talk offline. Yeah. I'll stop the